Today we're going to do a crash course on LangGraph, which is part of the LangChain ecosystem but operates on a lower level. LangGraph is mainly focused on agent orchestration, building workflows, modeling whole processes as graphs, whereas LangChain is more like a toolkit for building LLM applications, LLM wrappers, so to say. LangChain is more high level and simple, whereas LangGraph is more detailed and low level. So I would say, although it's probably not a hard prerequisite, I would recommend learning LangChain first. I also have a crash course on LangChain on this channel before learning LangGraph. As I said, it's not a hard requirement, but it's definitely beneficial to understand what agents are and how to work with LLMs in Python. In this video today, we're going to take a very hands-on approach. So we're going to work with examples, we're going to build stuff while learning, and we're going to introduce the concepts as we need them. We're going to cover many things like routing, conditional edges, human-in-the-loop approval. We're also going to do some RAG. So we're going to learn a lot today. It's going to be quite educational. If you like this video, let me know by hitting the like button and subscribing. And now let us get right into it. Alright, so we're going to do a crash course on LangGraph today. This is the website. As I said, it's part of the LangChain ecosystem. There's also a third toolkit called LangSmith, which is more for monitoring and serving, so for the whole MLOps side of things. But LangGraph is focused on agent orchestration, building complex workflows, modeling processes as graphs. That is what it's for. LangChain is more high level for building simple agent applications. LangGraph is for modeling complex processes and also durable processes. So we're not going to talk too much about the theory here. We're going to get right into the coding. For this, choose a directory on your system, navigate there. In my case, that's going to be the tutorial directory. And the setup is going to be quite straightforward. We need to install LangChain, we need to install LangGraph, and you need an API key to connect to some AI provider, LLM provider, because of course we need some intelligence powering the whole agentic system. In my case, I'm going to go with OpenAI. So what you want to do first is you want to create a file called .env, so .env. And in here, you want to put an API key. In my case, that's going to be OpenAI _ API _ key. Of course, if you use Anthropic, do Anthropic API key, Mistral API key, whatever is equal to, and then just put the key here. That is going to be our .env file. We're going to load the key from this exact file .env into our program. So in my case now, I have here the .env file, and the next thing is to install the packages. Now you can do that with your core Python installation. If you just want to install it globally, you can say pip or pip3 install LangChain, OpenAI, and LangGraph. But in my case, I like to have isolated environments. So what I do is I use the UV package manager. I will say UV init to create a project here. And creating a project is not fancy. It basically just creates a default main py file in the PyProject toml, which is basically the requirements txt file of UV. And instead of saying pip install, I say UV add. You don't have to use UV. If you use UV, this is how you do it. But feel free to use just pip install. It works the same way. Now, the packages that we're going to need are going to be obviously LangGraph, also LangChain with OpenAI support in my case, so in square brackets, and since I'm using Z shell, I need to also provide quotation marks, and we also need python.env to load the .env API keys into our script. So UV add these packages or pip install these packages, and then we can get started with LangGraph. And now before we write any code, I want to briefly visualize for you the process of LangGraph or the idea of LangGraph. I have MyPaint here, so I'm going to use that for a not so fancy visualization. What you need to understand that every process that we're going to build with LangGraph is a graph. So we start at a node called the starting node and we end at a node called the end node. Everything in between is whatever we decide it is. So in the most basic scenario, we would just have a simple node for prompting, so that would be P. So start would go to P, we would send a prompt to an LLM, and then we would get to the end state. That is the most hello world example that we can build, and it's also the one that we're going to start with. But in general, you can do a lot of stuff. You can have multiple nodes here, you can have conditional branches, you can say if something is the case, go here, go here, go here. You can loop into the same node, you can have a bunch of different branches, and it can get very complex if you want it to get complex. But the most simple example, as I said, is just start, prompt, end. And this is what we're going to build now in the beginning. So I'm going to go into main py here. I'm going to clear everything so we can start from scratch. I'm going to go full screen, and we're going to start with the import. So I'm going to say from .env import load.env. This is important to load the API keys. So just load .env like this. And then we can import from LangChain This is now not LangGraph, but we need to have a chat model. We need an LLM behind the scenes to do the intelligent work. So I'm going to say from langchain.chatModels, I want to import the init chat model function. And then from LangGraph, I need a couple of basic building blocks. So I'm going to say from langgraph.graph, I want to import message state or messages state. I'm going to explain in a second what the state is and why we need this messages state class. Also the state graph, which is going to be the graph itself, the main thing that we're building in LangGraph, and the two states that I talked about, which are uppercase start and uppercase end. These are two nodes that are going to be available by default, the starting state and the ending state. So let us start by simply defining an LLM. I'm going to say LLM is equal to init chat model, and I'm going to provide here OpenAI. Let's go with GPT 4.1 mini. And the next thing I want to do is I want to define a node for prompting. So the P that I showed you in my paint, just the center node that has some functionality. And for this, I'm going to say define a function prompt LLM. And it's very important now that this function takes in a state. The state is the current state of our graph. So we're going to pass the state from node to node, and this state contains information. By default, just a list of messages, which we can also set up in a way that messages are appended instead of replaced. But essentially you just have messages, but you can also define a custom state, which is what we're going to do later. And then you can put whatever you want into this state, and it's going to be passed from one node to the other. But for now, I'm just going to say state is the messages state. And all this function is going to do is it's going to generate a response by invoking the LLM. So response is equal to LLM.invoke. And we're going to get the current messages from the state. I'm going to show you what the state looks like here in a second, but we say state messages. That's a list of messages that already exist in the state. Now, I can go to the definition of messages state. This is a class from LangGraph, so we can take a look at the definition, and you can see the type hinting says it's messages annotated list any message. This basically means it has a list of messages in there, any type of message, user message, assistant message, tool use message, whatever. And annotated means we can pass metadata, and here we have the function add messages. You don't need to understand everything how it works in the LangGraph implementation, but basically this means that we append messages when we return them. We don't replace the messages list. So when one node returns a list of messages, it's going to be added to the existing list, not replace the existing list. So now we have the response, and we're going to do exactly what I just said. We're going to return a dictionary where we're going to say messages is going to be equal to a list containing response. So it looks like this would just overwrite messages, but since we have this annotation, it's going to be appended to the list of messages. And that is basically the only node that we're going to define. Now we can go and build the graph. And how we do that is we define a graph builder. So the state graph instance is going to be a graph builder, and the actual graph is what we get when we compile the graph builder. So I'm going to say here graph underscore builder is equal to state graph. I need to also pass the state, so the messages state class, so that we know what the state of this state graph is, what it looks like. And now I can easily just say graph builder add, and I can add nodes and edges, and also conditional edges. We're going to talk about this later, but for node, I'm just going to add now the function that we defined as a node. So prompt LLM, and a node always takes in a state and returns something. In this case, we take in the state, messages state, and we return our response, and this appends it to the state. So now what we need to do is we just need to connect the nodes that we already have. So I'm going to say graph builder add edges or add edge. I'm going to say from the starting node, I want to go to prompt LLM, and from prompt LLM, I want to go to the end node. That is the most simple setup that we can have. To now get the actual graph, I'm going to say graph is equal to graph builder dot compile. This is going to give me the graph instance, and the only thing left to do is now to use this workflow. So I can say user message is equal to input, and then I can say enter message. That's going to be just a user input, and then we can feed that through the graph by saying graph invoke, and we're going to pass a list of messages, just messages, and here dictionary, typical format that we know from every implementation. Role is going to be user, and content is going to be whatever the user entered, so the user message. And of course, to see something, we need to print the result. Of course, we can also target just the content field, but let's just see what the entire thing looks like. And keep in mind, since we're doing this only once, it's going to jump to the end state. So this is not going to be a conversation that we keep going. Let's see what happens when I run this, uv run main py. Otherwise, of course, do python main py. And of course, I made a mistake here because we add the node by passing the function, but we still refer to this node by the name. So it's going to take the name of the function, which means that we need to refer to it when adding edges. We need to refer to it as prompt LLM, the string, not the function instance. So then let's go uv run main py, and I can say hello. And you can see as a result of that, I get the AI message in here in the messages key value pair, and it says, hello, how can I assist you today? And the script ends. Now I can also do a while true loop around it. So I can say while true, do this thing. And this would work. It would allow me to repeatedly send messages by invoking the whole graph every single time, but there's not going to be any context. So if I say, hello, my name is Florian, for example, and then the next message I ask it what my name is, what is my name, it's not going to be able to tell me that because it doesn't have any context. It will tell me I don't have access to any personal information about users unless you share it with me during our conversation, implying that I didn't do that because it's a new conversation. So if we want to fix that, what we can do is we can add a check pointer. We can add memory to our graph or to our model, and we need to pass the context just in every interaction with this entire graph. To accomplish this, we go up to the imports and we say from langgraph.checkpoint.memory import the in-memory saver. We also have alternatives here for SQLite and Postgres. We're just going to go with a simple in-memory saver here, and that is going to be our check pointer. So I can say here check pointer is equal to in-memory saver. And then when compiling the graph, I pass this check pointer here. So I say check pointer is equal to check pointer. And in addition to that, now I can pass a config object, which has to have a certain structure. So I can say config is equal to, the first key has to be configurable. And this points to another dictionary where I have a thread ID, and the thread ID has to be whatever. I can call this hello world if I want to. Professional would be to use a UUID. So let's say import UUID here and go back down. We can just say UUID.UUID4. And the important thing is it's always the same. So if you pass the same thread ID, it's going to consider this to be the context. So that's fine. Just pass it like this. And the only thing left to do now to get the context is when invoking the graph, we need to pass the config object. So we pass the messages dictionary, and we also pass config equals config. This is going to keep the context. If I now say uv run main py, every time I invoke the graph, I still have the same thread. So if I say, hello, my name is Florian, and then I ask it again what my name is. What is my name? You can see, first of all, the whole resulting object is larger, and then you can see the previous messages are stored. And down here, you can see your name is Florian. How can I help you today? So this actually kept the context. If I may for a second, I would like to plug myself in as the sponsor of my own video. If you go to my website, neural9.com, you will find a tab services and a tab tutoring. Here you can hire me for all sorts of stuff like data science, machine learning, web development. If you need help with something in a project, here you can book me for one-on-one tutoring. If you want me to teach you personally something that you don't understand, if you like my teaching style, on both pages at the bottom, you can contact me via mail and also via LinkedIn. Just wanted to let you know about this. So that is the very basic and trivial example that is very useful to get started with LangGraph. I now want to move on to the main example of this crash course today because it's going to illustrate a number of interesting concepts. And for this, I'm going to go back into my paint and briefly sketch it out, not in a very professional way. But again, we have, of course, start and end in the beginning and in the end. And our workflow that I want to build in this video today is going to be the following. We're going to have a user prompt. So the user is going to enter with a message. This is going to go to a classifier node. Classifier means it's going to classify the intent of the user message. This can split into 3 different possible classifications. The one is going to be the user just wants to have a chat. I'm going to say CH for this one. Another one would be the user is asking for a knowledge request. So we're actually trying to retrieve some information from a database, or it's going to be a coding request. So I want to make a change in a code base. Now, depending on what I choose, I'm going to be led to different nodes. So this is going to be the classifier. I'm going to have conditional edges here that are going to throw me to different nodes. And if I get to this one, I'm going to just be sent to a chatting node. Let's call this P again for prompt. It's just going to have a conversation with me and then lead to the end node. For the knowledge request, we're going to be led to a RAG node. So this is going to do retrieval augmented generation. Very, very simple. We're just going to have a knowledge base, retrieve some information from there, and then return. And the most interesting one is probably the coding one, because what we're going to do here is we're going to have a coding agent. It's going to be Claude Code in headless mode. And the interesting thing about this, it's not just going to do a change, it's going to ask for human in the loop approval. So I'm going to say here, Claude Code is going to try to make a change. And this is going to lead us to a human in the loop, if I want to call this HIL here, human in the loop approval. If we approve this, it's going to get it done and lead to the end node. Otherwise, it's going to reject it and lead to the end node. Or I can also go back. So we're going to loop this back here and say, I want to revise my prompt. And then I go back into this human in the loop approval process. And then finally, to make this even more complicated, we're going to add an additional node here that is going to formulate the prompt for Claude Code. Because maybe I tell the agent, my name is Florian, and then I tell it, write my name into the README file. And of course, if I just pass the raw prompt to Claude Code doesn't know my name. So I expect the entire graph agent here to be able to pass the proper prompt to Claude Code. This may sound very confusing, and we're not going to build all of this at once. We're going to start very simple by introducing one concept after the other. So I'm going to start by just having this classifier and the conditional nodes that are going to print 3 different messages and then all lead to end. And we're going to step by step extend the functionality of this graph. So let's go back into our main PY file. We're going to keep some of the stuff. I'm going to remove a lot of it. Let's get rid of all this. Let's also not import messages state anymore, because I'm going to define now my own custom state as a class. For this, I'm going to need a core Python package. I'm going to say from typing import. I'm going to import typed dictionary. I'm going to import annotated, and I'm going to import literal. We import annotated and typed dict because that is how the messages state is also defined, because we also want to be able to append messages, and literal is going to be for structured output. So we can force the specific intents to be chat, knowledge, and coding. Now, to do the structured output, of course, we also need an additional package, which is Pydantic. I assume most of you guys know Pydantic already if you have worked with LangChain before. So uv add Pydantic or pip install Pydantic, that's going to be important to define the schema for our structured output. And we're going to say from Pydantic import the base model and the field, of course. And maybe let's restructure this here. And then one final import is going to be the add messages function. Remember, the messages state had this annotation with add messages. We also need this add messages to allow for the appending of messages. So from langgraph.graph.message import add messages. All right, and now we can define, first of all, again, our model. This is going to be the same as before. Actually, I shouldn't have deleted this, but it's not too much. So OpenAI GPT 4.1 Mini is going to be the model powering the whole workflow here. And then we can start by defining the structured output schema and also the state. So I'm going to say here, class intent classifier, going to be base model, and it will have the intent that we want to classify. So I'm going to say here intent, or let's call this message intent. And that is now going to be a literal, which can have one of 3 values. We're going to say chat, we're going to say knowledge, and we're going to say code. And we can also describe this by saying fields, ... And the description is going to be, I'm going to copy paste this one here, classify whether the user wants to just chat, ask for knowledge, or change code in the project. One of the 3 has to be the case, and it's going to determine to which node we go next. Then we need to define a state. So the state is going to be our own custom state. It's going to inherit from type dictionary. We're going to basically do the same thing that we did with messages state. If you don't know what it looks like, if you don't remember, you can import it again and just go to the definition. However, you do that in your favorite editor. But remember, this was messages state, type dictionary, and here we had annotated. And yeah, it was basically formulated like this. We're going to do it in a very similar way here. We're going to say messages is equal to annotated. We're going to keep it simple. Just say list and add messages, just to not have it too complicated here. Also want to have the message intent. This is important because we also need to pass this from node to node. That can be a string or it can be none in the beginning. We don't have this out of the box, so maybe it has to be set later in the flow, but that is also part of our state. So then let's go ahead and write the first node, which is going to be the classify intent. I'm going to say define here classify intent. Of course, this is going to take in a state, which is going to be of type state. And by the way, you can put in whatever you want into the state. You can also say, I don't know, favorite food and pass it from node to node. Doesn't really matter. You can just define stuff and pass it here. But classify intent takes the state and does an LLM prompt with structured output. So first of all, we are going to create a structured instance. I'm going to say structured LLM is going to be equal to LLM with structured output. And here we need to pass the pydantic schema intent classifier. And then we can just do the same thing as before. We say result is equal to structured LLM dot invoke, and we can pass a system prompt and a user prompt. So I'm going to pass a list here. First dictionary is going to be role system. Here we're going to instruct it how to handle this request. The content field is going to be the following: determine, classify whether the user wants to chat, retrieve knowledge, or change code. And here we have the exact strings, but we also force structured output, so that's fine. And of course, from the state now, we need to get the user prompt. So the next message here is going to be with the role user. And the message is something that we need to get from the state. So user is going to be the role. And the content is going to be taken now from state. The last message that was sent is going to be the user message. So state.messages, -1 to get the last one, .content to get only the text. And of course, you need to spell it correctly, content. So this whole thing will result in an instance of intent classifier. So we need to access the message intent field and return this as a dictionary so that we update the state. So the message intent in the state shall now be result.message intent. So this is the classifier. Now let's define the 3 nodes that we can end up in. And for now, we're just going to print different messages. They're not going to have any fancy functionality. Let's say prompt LLM chat. I'm going to call it like this, state. And we're basically going to do a very similar thing, not with structured output. Actually, let's do it manually here. We're going to say messages is equal to, and it's going to be a list. We're going to start with the system message. So I'm going to say here, role is system. And depending on what node we're in, we're going to have a different system message for now. That's going to be the only difference. Content is you are a talkative chatbot for fun. Be nice. That's going to be the chat node here. And in addition to this messages list, we're also going to say plus state and the entire messages list. So whatever we had in there is going to be appended to the end. So if you want to see this in one line, this is what it looks like. And now what we want to do is we want to take this messages list and say response is equal to LLM invoke on these messages. And then of course, we just need to append the assistant response. That's going to be the response content. So here we're going to say return, and to the messages we want to append now as the following, in the following structure. Role is going to be assistant, and the content is going to be whatever we got here. So that's going to be content pointing to response.content. And of course, since we're appending here, or since we're extending, we need to pass this as a list. So like this. And basically now we can copy that and do this 2 more times. So it's going to be prompt LLM chat. It's going to be prompt LLM rack, and it's going to be prompt LLM code. And the only difference here is going to be the system prompt. I'm going to say no matter what the user says, always say I am the rack agent. And then basically we can copy this, paste it down here, and replace rack with coding. Just so we know which bot we're currently talking to. If it doesn't say any of the 2, it's going to be the chat bot. These are now the 3 nodes. And now the question, of course, is how do we wire all of this up? How do we take the intent that the classifier returns and route to the proper node? For this, let us start by creating the graph again. So graph_builder is going to be equal to state graph, taking state this time, not messages state. And we're obviously going to do the same thing that we did the first time. We're going to add the nodes. Now this time we're also going to provide the name. So I'm going to say classifier is going to be, sorry for the jump, classifier is going to be pointing to classify intent. That's going to be the name of this. Then we can say chat agent is going to be pointing to prompt LLM chat. And then also rack agent is going to be pointing to prompt LLM rack. And then finally, the coding agent is going to be pointing to prompt LLM code. Then also nothing fancy is going to be just a simple edge from the start to the classifier. That's, I think, clear why we do that. And the next thing is to do a conditional edge now from the classifier to the other nodes. So depending on what the classifier returns, we want to jump to a different node, and we can do that with a lambda expression and a dictionary for the mapping. So I'm going to say here graph builder add conditional edge. I'm going to say going from classifier, I want to have a lambda expression decide. It's going to take in the state, and in the state there's going to be the message intent. So think about it this way. The second argument is a function that takes in a state, returns the message intent of the state. And then the third thing here is a dictionary that maps the result, so the intent, to a specific node. So if the intent is chat, we're going to jump to chat agent. If the intent is knowledge, we're going to jump to the rack agent. And I'm not sure if my camera is blocking this, so let me put this up. But that still has to be a string here. And if the intent is code, we're going to jump to the coding agent. And then the rest is quite simple. I'm going to just say graph builder add edge, and it's going to be going from all of these. So from the chat agent to end, and we're going to do this 2 more times with the rack agent and with the coding agent. The rest is basically the same as before, but let's repeat it so it sticks. So we're going to start by saying the check pointer here is equal to in memory saver. We're going to say graph is equal to graphbuilder.compile. And we're going to pass the check pointer here for context. We're going to have a config object again. Remember, we have the first key configurable pointing to a second dictionary, which contains a thread ID, which is going to be a UUID 4. And then we have our endless loop while true. User message is going to be some input. So we're going to just say enter message. And the result is just going to be invoking the LLM, or invoking the graph in this case. Graph.invoke. I'm going to pass here messages being a list and containing one user message. So the role is going to be user, content is going to be whatever the user entered, the user message. And of course, don't forget the config. So config is going to be equal to config. And at every point, we're going to print the result message. So result messages -1 dot content. So the last message, just a text. If I didn't make any mistakes and typos, this should now work. So uv run main py. I can say hello. Okay, so it looks like we have an error here. Let me take a look. We have line 31 state messages. That should maybe be a dictionary access, key value access. So I'm going to say here that is going to go for messages. And also, I think I made a mistake here because we should not use equal signs. Obviously, we should use colons. So that is how you define a type dictionary, same as a pydantic model. Let's go now, uv run main py. Hello. And this should now be classified as a chat intent, which is why we get a message, a normal message. So let's say now, tell me when my birthday is. Hopefully this is going to be taken as a knowledge request, maybe not. So look up the database and tell me the date. So that should be a knowledge request now, and it says I am the rack agent. So if I say, please change line 112 in main py, this should be recognized as a coding intent, and it should say I am the coding agent, and it does. Perfect. So this routing works. Let us next add the actual functionality. So for the chat node, we're actually done. That's going to be it. We're just going to return an answer and that's it. But for the rack, we want to have an actual knowledge base. Now for this, I'm going to copy paste just a list of strings up here. I'm going to say knowledge is equal to, and then Neural 9 is a YouTube channel focused on programming, AI, and software engineering tutorials. And then some other stuff here about LangChain, basic stuff. This is going to be our knowledge base. And we're going to use a LangChain vector store here. So for that, up here, I'm going to say from langchain_core.vectorstores, import the most simple one, the in-memory vector store. Then from langchain_core.documents, we're going to import document. That's going to be the instance here for the knowledge base. And of course, for the vector store, to be able to put something into it, we need intelligent embeddings. For this, we're going to use an OpenAI embedding model, so we don't have to use different keys. So from LangChain_OpenAI, we're going to import the OpenAI embeddings. So that's now more of a LangChain tutorial. This is not really LangGraph related. We're nevertheless going to do it. I'm going to say vector store is going to be equal to in-memory vector store. We're going to use the OpenAI embeddings model. And to be precise, let me see what I used in my prepared code. It was text embedding 3 small. So that's going to be the model that we use to create the embeddings. And the simplest way to fill this up is to just say vector store add documents, and then we can do a list comprehension, documents. And in this document, the page content is going to be equal to text for text in knowledge. So that's super simple. Let's go down now to our rack node. The only thing that we have to change is going to be in this node. So we're going to get the last user message. I'm going to say query is equal to state messages. And that's going to be the last message, so -1. The content of that, that's going to be our query. And now we want to get the documents that are the most similar. And for that, we're going to do vector store similarity search given the query. And we're going to go for the top k being equal to 3, retrieve the 3 most relevant answers. That's going to be our documents. Then we're going to craft our context. So we want to get the document information, put it into context, and then we're going to send a message with the context, with the system prompt, and with the user question. So I'm going to say \n join, and a formatted string, make it a bullet point here. We're going to say document. So let's say doc.page content for doc in documents. That's going to be the context. And for the messages now, let me copy paste this because I don't want to type this now. It's basically the same idea. The only thing is that our messages now are, or our system message here is now you're a rack agent. Answer the user using only the context below. If the answer is not in it, say you don't know, context, and then we pass the context that we just crafted. That is going to be our rack node. Now, 2 more things that we need to do for this to work. One thing, I realized that I didn't pass this properly. It has to be a keyword argument. So we need to say model is equal to text embedding 3 small, not just passing it. Otherwise, it's not going to work. And for the similarity search to work, we also need to install NumPy. So do uv add or pip install NumPy here, because that is not automatically installed with the other packages. And then we can say uv run main py. This is going to ask me for a prompt. We can ask for a very basic piece of information like who is Obama. This is a super simple prompt. Every LLM is able to answer it, but it's probably going to tell me I don't know, because of course it did rack, it wasn't in the context, so it's not going to answer. If I ask who is Neural 9, it should know that because that's directly in the context, and it should give me the response. Neural 9 is a YouTube channel focused on programming, AI, and software engineering tutorials. So the rack node now works. Let us tackle the coding node. For this, let's create a directory called workspace. Here, we're going to work with Claude Code. And just so it has something to work with, let us go and create a readme.md file, which is just going to contain hello world, just so we have something to edit. And now we're going to go back into our main py code and go to the prompt LLM code node. Now, of course, for this to work, you need to have Claude Code already set up on your system. I'm not going to cover it in this tutorial here. We also need to import a Python package called subprocess. This is core Python, allows us to run commands on our system. And we're also going to need the OS package. So input OS, import subprocess. And then we're going to say that the user prompt is equal again to state messages -1 to get the last one, and then .content. We're going to define our workspace path. So workspace is going to be equal to OS path join, OS path directory name of OS path absolute path of this file here. So __ file underscore underscore. That's going to be just a parent directory of this main py file. And in that parent directory, after it, we have the workspace directory. That's how we concatenate this. Of course, you can also hard code the full path if you want to. And then we're going to get rid of this. And we're going to say result is equal to subprocess.run. And here we're going to now define the Claude code command. So I'm going to say, first of all, I want to run Claude-P. That is for headless mode, so we don't have to interact with it. The prompt is going to be the user prompt. So whatever the user type, we're going to feed directly into Claude. Later on, we're going to make this more sophisticated. For now, we're just going to feed the raw prompt to Claude Code. And important, we need permission mode to be equal to allowing edits. So accept edits is the permission mode. Otherwise, it's not going to be able to change anything. So maybe let's go and put this into one line because we're going to have other arguments here as well. These are going to be, for example, the current working directory, CWD, that's going to be the workspace. We're going to say capture output equals true, and we're also going to say text equals true. And then the output is going to be result.standard output, so std out strip. We're going to take whatever is in std out, we're going to take this, strip this, and if there is nothing, we're going to say result.stderror.strip. And instead of passing response content, here we're going to pass output. So the basic idea is we get the user prompt, we define a workspace, we run Claude Code in headless mode with the user prompt, we get some output. If we get some output in std out, we just take this as output. Otherwise, we get the error message, and that is our response from the assistant. So this should already work. Let's go out and say uv run main py and ask it to add something to the file. So please add 123 to readme.md. And of course, we should spell permission mode properly. So let's go down here again to the note and say permission dash mode, not permission mode in camel case. uv run main py. Please write 123 into readme.md. And it just says written. So let's see if that actually happened. Let's go into the workspace and open up the readme.md file. And you can see 123 is in the file. Now it overwrote the hello world. Maybe I wanted to add it, but it doesn't really matter. It did the change. So this also works. However, this coding process can be a bit tricky or risky. So in this case, we might want to implement something called human in the loop, which means that before we actually do the coding step, not going to be true for the RAG, not going to be true for the chatting, but if we want to do coding, a human needs to manually approve that this actually happens. So I want to be prompted with a yes or no question. Do you really want to execute this coding command? And for that, the first thing we need to do is go back into main py and do an import from LangGraph types. We need to import interrupt and we need to import command. And our interrupt now, or our accepting, will be handled in a separate node. So we're going to add an additional node here, which is going to be called accept coding. Also going to take in state, of course. And here now we're going to interrupt the flow, interrupt the workflow of this graph and force the user to give a response, to give a decision, to make a decision. So I'm going to say user prompt is equal to state, as always here messages -1 content. And then I'm going to interrupt. And I'm going to interrupt with a message. This message is going to be about to run Claude Code with request, user request, or actually user prompt. I named this differently in my prepared code. Approve, yes, no, or type a revised request. That is going to be the message, and the decision is going to be saved as a response. So the interrupt is going to happen, we're going to have a decision, and then based on that decision, we're going to return different values. So we're going to say text is equal to the string version of the decision, strip it from all white spaces and so on, and then also dot lower. And then we can say now if text in, and we can define a specific list of exact strings that mean yes. We can say Y, we can say yes, we can say approve, we can say okay, whatever. You can define exact strings that mean yes. And in those cases, we can just return an empty dictionary. Otherwise, we're going to check if the answer is no. So if the answer is in N, no, deny, or cancel, that's going to lead to a rejection. So in this case, I'm going to send a basic response here. That's going to be coding request was denied by the user. But very important now, in addition to this is just appending to the messages object. But in addition to this, now we need to pass something else to our state. So for this to actually work, we need to extend our state in the first place to allow for a field called next node, because we need to be able to control where the next jump is going to happen based on the state. So I'm going to say the next node is either a string or nothing. And in the case now of this node actually resulting in denial, we're going to say that the next node is going to be denied. And in all other cases, we're just going to send the text that the user typed as a prompt back. So I'm going to return here with a user message. So messages, role user, content, and the content is just going to be the text. That means it's going to reprompt the agent. Here we're going to deny, and here we're just going to return an empty dictionary. So what's the logic behind this? We're going to add a conditional edge, and if this returns next node denied, we're just going to jump to end. Otherwise, we're going to just go with an empty dictionary because we're going to have the same last message that is going to be used in the coding node. So here in our prompt LM code, we get the last message. If we just want to keep the message, we don't have to do anything. We're just going to go with the same last message. Otherwise, if we have to type something new, we're going to take this message directly and feed it into the coding node here. So now what we need to do is we need to say graph builder add node, and we need to add our additional node here called accept coding, which is the function accept coding. And we're going to add a conditional edge here, graph builder add conditional edge from accept coding, also with a lambda expression state, and we're going to return end if the state, let's say get, because otherwise it might fail, get if this next node is equal to denied, then I want to return the string end. Otherwise, I'm going to return the string coding agent. Now, finally, one last thing that we need to do to actually make this work is we need to handle the interrupt in the while true loop. So this interrupt up there is not going to automatically prompt us and respond to our input. We need to handle it here. So we need to say after getting the result from the invocation, while there is the key __ interrupt, while this exists in result, I want to handle this. So I'm going to say prompt is equal to result. And then we're going to get this key interrupt here, index 0 dot value. And now we want to get the user input. So decision is going to be whatever the user inputs after being shown the prompt. So we're going to say here prompt and then maybe an angle bracket and a space. Maybe let's also add a \n. And then we need to take this decision and feed it back into our graph. That's going to be done with a command. So we're going to say result is equal to graph.invoke. And we're going to invoke here a command. And the command will be resume equal to decision. So whatever we input is going to be passed using this command to our accept coding handler. So if it's a Y, if it's a yes, it's going to be considered a yes. If it's an N, deny, or whatever we defined, it's going to be a no. And important to keep context, don't forget to pass the config as well. Always pass the config. And also, of course, one very important thing that we should not forget, right now our classifier immediately routes our coding intent to coding agent. That should not happen. We need to reroute this to accept coding first. That's important. We need to route our code intent classification to accept coding and only if accepted to the actual coding agent. So let's go now and run uv run main py. And let's type a prompt like please change the content of the readme file to hello neural 9, for example. This should now give me an approval request. There you go. About to run Claude code with request. I see my prompt, approve, yes, no, or type a revised request. Let's go with yes. And this should now just take this prompt, apply it, and that's it. If I say no, it should stop. It should break out of this. And if I type a revised request, it should do whatever I typed there instead. There you go. Updated readme.md to hello neural 9. Let's see if that's actually the case. Workspace, readme.md, hello neural 9. This worked. Perfect. Now let's try to do the same thing here with a no. So let's say, please edit readme.md to be hello YouTube or something. Now I'm going to say no, and you can see coding request was denied by the user. Now, one thing that you will notice is that this human in the loop approval is not perfect, because if I say now, please edit readme md to say hello YouTube. Then if I type something else like, let's say, please edit readme md to say hello Twitch or something, then that is going to be taken and executed automatically. So it's not even going to ask me for another approval. It's just going to take that and replace it immediately. So we don't have a loop process here. We do have a human in the loop, but we don't have a loop until you finally approve with the yes. And there you go. You can see I have updated readme.md to say hello Twitch. And if I look at that, we're actually going to see that the readme now contains hello Twitch. But before we actually fix this now, I want to show you how we can visualize our graphs, because I think this is super interesting to see what it actually looks like to look at our flow. And for this, of course, we need to first build the graph. And after building our graph, we can say graph.getGraph. And then this will have a draw mermaid PNG. And here we can say output file path is graph.png. Just to show you what this actually looks like right now, UV run main py. We can immediately break out of this and see if we have now a graph PNG. Use your favorite image viewer. In my case, I'm going to use Nomax for graph PNG. And this shows me now what our flow looks like. We have the start node. It goes to the classifier. It can go to code, chat, knowledge. Then we have accept coding here. And if we accept, we go to coding agent, or if we type anything except for no or deny or end, we go to the coding agent, then we go to end. Here we do rack and chat, and everything ends up in the end state. And in this context here now, what we want to do is we actually want to say, if there is a revision, go back to accepting. So go back with that new revision to accepting, and only if that is now accepted, go to the coding agent. So the only thing leading to the coding agent should be a yes, otherwise loop back into accept coding. And that, of course, can be done in a very easy way. So let's go back into our code. The only thing we need to change is our accept coding class here, or our accept coding node. In this case here, if I say yes, we want to go to coding agent. So I will actively pass the next node here to be coding agent. Of course, this doesn't touch the messages. We're just updating the next node. And here now, I also will say that the next node is going to be explicitly defined. So it's going to be the accept coding node. So now we have, if I say no, we go to denied. If I say yes, we go to coding agent. If I say something else, we're going to go to accept coding again. And then down below at the conditional edge, we can basically say that we get end if the next node is denied, otherwise not coding agent, but whatever the state has, whatever the node is, state next node. And we're going to map this. It's going to be end to end, coding agent to coding agent, and accept coding to accept coding. Let's see if this works now. UV run main py. And here now I'm going to say change the readme content to 2 + 2. Now it asks me, do you want this? I'm going to say no, or not no. I'm going to revise this. I'm going to say change the readme content to 4 + 4. And now you can see I'm looping back into this accepting node. And if I say yes, it's going to apply 4 + 4, not 2 + 2. There you go, updated readme to 4 + 4. And if I take a look at it, workspace readme, that is 4 + 4. So now again, we can take a look at the graph with Nomax in my case here, and we can see that this looks different now. We have accept coding going into itself. So we have a loop here, which results in different behaviors. So we have accept coding going back to itself, or to coding agent, or directly to the end. Now, one more thing that we want to do here is we want the agent itself, or the LLM, to prepare the prompt, because right now we have a problem. If I talk to the LLM, so if I start a conversation here, UV run main py, for example, because I'm chatting, I can tell it about my name. Hello, my name is Florian. And it will recognize that, it will remember that. If I ask what is my name, it will be able to answer that my name is Florian. However, if I tell it, write my name into readme.md, it doesn't have the context, because what's happening now is my request directly is sent to Claude Code, and the prompt is just write my name into readme.md. Claude Code doesn't have the context of my name, which is problematic. So what we have to do here now is we want the agent to craft the prompt that we then feed into Claude Code. I still can approve it, but the agent crafts it for me so it can include all the context that it has. So for this, let's go back into our script. For this one, I'm going to do copy pasting because it's just another node. It's very, very simple. Nothing new to learn here. We're going to call this one prepare coding request. It literally does nothing fancy. We just have messages. We invoke the LLM and we append the response. As simple as it gets. But it says here, rewrite the latest user coding request into a clear instruction for Claude Code. Use the conversation history as context, only output the instruction, no explanation. And now, of course, we need to take this, turn this into a node, and we need to do some rerouting. So instead of going to accept coding directly, we first go to this node. So I'm going to say graph builder add node. And the node that we have here is going to be, what did I call it? Prepare coding request. We're going to have the function prepare coding request. And we now just need to make sure we route to the proper thing. So accept coding, or even before we get to accept coding, classifier needs to go to chat agent, rack agent, or in the case of code, to prepare coding request, and prepare coding request needs to then go to the accept coding. So we're going to add an edge down here, or maybe up here, graph builder add edge from prepare coding request to accept coding, because that's going to lead into that. And also one more thing, if we go from accept coding back to accept coding, we actually want to go back to prepare coding request. So let's see if that works. I'm going to clear, I'm going to run main py, and I'm going to ask again, or I'm going to give the information first again. Hello, my name is Florian. Now it has that context. And then I'm going to ask it, please write my name into the readme MD. And you can see now the Claude request is add the following line to your readme MD file, Florian, as a heading. Approve, yes or no. The cool thing now is I don't even have to type the next request. I can say, please don't make it a heading, and it won't just take that and feed it into Claude Code. It will actually take that and revise the prompt and show me the new one. So here you can see add the following line to your readme MD, just Florian, without anything else. Now I can say yes, and this is going to be approved. And now if I take a look at the readme MD file, we can see it contains Florian. So that worked. Now finally, let us take a look at our graph one more time, at graph PNG, which is always being exported since we have the line in our code. And this now looks already quite interesting. We have the start node going to classifier. These two branches are quite basic. They go to chat and rack. And here now we have a professional loop. We have the prepare coding request, sending it to accept coding. This is the human in the loop process. We can revise. In this case, it goes back to prepare coding request. Maybe we should change the values to be revise, deny, or accept. But basically, we have accept coding here, going back to prepare coding request to go back to accept coding. If we deny, we go immediately to end. And if we approve, we go to coding agent and then to end. So yeah, I think that's enough for a LangGraph crash course. We learned quite a bit today. So if we look at the file, we applied a couple of concepts. We did some stuff with LangChain too, like RAG, for example. We used embedding models. But more important than anything else is we know how to work with conditional edges, how to create nodes, edges, state graphs, how to create custom states and pass information, how to work with structured output. And this is what LangGraph is all about. Modeling workflows, having stateful agents in a very professional and low-level way. So that's it for this video today. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. Also, in case you're interested, on my website, you will find a services tab and a tutoring tab. There you can contact me if you need help with a project, if you need a freelancer, consultant, someone to build stuff with. You can contact me via LinkedIn or email at the bottom of these pages. Besides that, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you for watching. See you in the next video and bye.